Hello! Today we will look at some applications of ordinary differential equations. And we will start with one application that everybody shows, and we will shortly see why, because it's a very nice application. Let's move over here. It's actually an example from physics, and here we have pendulum, which we can of course swing to the left, to the right. There are some assumptions needed. So here we have a rod which has length L, and we will ignore the mass of this rod. Otherwise, the situation will be very complicated. So we don't want that. We are going to ignore friction, which is over here in this joint. Another complication, we don't want that. So we will just assume that the mass is all concentrated here in this ball. There's a mass m. And we will have to somehow measure the position of this pendulum. And traditionally, we will look at this angle. Let's call it theta. It's a nice Greek letter. OK, here we go. Now, when we are deriving differential equations, we typically ask for influences. So what is the influence over here? Well, gravity. If we didn't have any gravity, then the pendulum would simply stay in this position. So the gravity is pulling down on the weight. And we have a force here, F, which is equal to m times g. This is elementary school physics. Now, this force, of course, is trying to do all kinds of things, but it cannot do them because this pendulum is restricted in its movement. It can only go in a circular fashion. So this force actually splits into two components. One of them is leading in the direction of this rod. This is so-called radial force, and this one doesn't really have any effect. What it really is trying to do is to pull this pendulum out of the ceiling. And hopefully it's strong enough to stay there. So this part of the force is essentially wasted. If you were really careful, you would have to talk about this friction here, and this force is actually increasing the friction, but we are ignoring that. The other important component goes like that. It's tangent to the movement of the pendulum, which goes in a circular fashion. And this tangent component of our force F is exactly the part that we are interested in, because this part is trying to move the ball to the left in this picture. If the pendulum is over here, it's trying to move the ball to the right. So what is the magnitude of this force? We have a nice rectangle here, and there is an angle, theta, which is also carried over to this place, but also to this place. So when we look at this triangle, we can see right away, we can use the sine function. It's this divided by this magnitude gives me sine of theta. And therefore, the force, which, OK, let's call it, let's say, F tilde, that's the one that we want. So F tilde will be just force F times sine of theta. OK, now what does a force do? The answer is it's actually imparting an acceleration to some object. So there will be an acceleration happening here. Let's call it A, which is force divided by mass. And now when we substitute for F into the formula, we can see that this is really just g times sine of theta. Okay? Just out of curiosity, does it make sense? Okay, if the ball is over here in the downwards position, then sine of theta is sine of 0. It disappears, which is okay. And we can see that the force really pulls down, not to the side. So this agrees. It makes sense. Okay, that's the acceleration. Now, there is another way to achieve acceleration or to reach acceleration through the position. When we look at the position of the ball and differentiate twice, we get acceleration. So let's have a look at it. What's the position? Well, the position depends on the angle. It's another of those famous things from elementary school. If you know the length of the rod, if you know the angle, then the displacement here, but this is like a circular displacement, is L times theta. Now when the pendulum is moving, it's exactly this quantity which is changing. So if I differentiate it twice, I should get the acceleration. And of course, L is a constant, so I'm just getting second derivative of the angle. We have to be careful. The displacement is measured in this direction because the angle is measured in this direction, but this gravity action goes in the opposite direction. So when we want to compare this and this acceleration, we have to change the sign. And it goes like that. Finally, we can rearrange a little bit. I'm going to divide by L, move this term to the left, and I get this formula. Second derivative of the angle plus G over L, sine of the angle, should yield 0. And that's a simplified equation of a pendulum, simplified because we didn't consider mass of the rod, we didn't consider friction, things like that, but all the important factors are in it. And then it's traditional to take this number and call it omega squared. It's also traditional to use a different letter in physics. Rather than theta, people use y or x. I'm going to use x. And we get the first important differential equation for today's lecture. It goes like that. The second derivative, and let me put it with dots. That's a nice physical notation. So the second derivative plus omega squared sine of x is equal to 0. That's a second order differential equation, but it's not linear. You can notice function x, the unknown function, is inputted as an argument of sine function. So this is definitely not linear. I would call it exact pendulum equation. And this exact pendulum equation has one little problem. We cannot solve it analytically because of the sine function, which is unpleasant. So we can say, okay, wait a second. Let's say that this pendulum does not really move much. If it moves just a little, just a few degrees to the left, to the right, then we know that the sine function can be approximated using the tangent line. We can simply drop the sine, and we get almost the same answer. The error will be negligible for really small movements of the pendulum. And in this way, we arrived at a new differential equation, which looks like this. Second derivative of x plus omega squared times x is equal to 0. And let me put some labels next to this differential equation. This one is actually very popular, very useful. So it has special names. Let me start with this one. Instead of exact pendulum equation, I would call it approximate pendulum. I could also call it mathematical pendulum. Equation. Because this simplified version is sometimes called a mathematical pendulum. So you've got real pendulum, it moves in a certain way, and you've got a mathematical pendulum, which is a model. Virtual pendulum, which moves in a slightly different way, perhaps because instead of sine of x, we are taking just x. And as I said, for small values of x, we hope that these two should be more or less the same. This equation also has another interpretation, which is also very nice. So we've got a ceiling, just like before, but this time instead of a rod, we put a spring there. And at the end of the spring, there will be some mass. Again, we are going to ignore the mass of the spring itself. Now, there are two forces, gravity and the spring force going upwards, and in a certain moment, at a certain position, they both even out. So the gravity force, the spring force, they are the same, just in opposite directions, and you got the moment of equilibrium, and that's the reference level. And now we will displace this mass from this reference level, from this equilibrium position, and we see what's happening. So we can measure it using some function, let's say x. I actually slightly prefer now to have it pointing downwards, but it doesn't really make much difference, okay? It just allows me to make a nicer picture. So I'm extending the spring all the way here into a new position, and I'm asking, what's happening here? Well, what are the influences? Again, that's a good question. Well, there is the gravity, but the gravity is actually neutralized by the spring. So the only force which is left is the spring force, because by pulling on it, we actually increase the influence or the effect of the spring. And there is again, we have to go to physics, ask about it. What they say is that this force is actually proportional to the displacement, which is x. That's the advantage of setting 0 at the equilibrium position, okay? Because then there is no extra force for the spring. It only appears if you pull it or perhaps push it up. So that's the force acting on this mass. And of course, we can recover it also as a second derivative of the position. So we are getting that the second derivative of x, well, actually, let me put the dots. Second derivative of x is exactly, and now we have to be careful, we have to take the force and divide it by the mass of this object over here. So we get k divided by mx. And then we again have to ask about the directions. F is pointing upwards, x is pointing downwards, so we have to put minus here. Okay. Now we look at this equation, and we notice that if we take k over m, square root of it, and call it omega, then this becomes exactly the same equation as we have over here. So this is also an equation of a mass on a spring. That's how they call it in physics, mass on a spring. I'm too lazy to write it down, so I will just put a spring equation. So as you can see, this equation actually serves more purposes, and it has a special name. If some phenomenon is moving according to this differential equation, then it's called harmonic oscillation. So that's a name which is attached to this type of differential equation. That's not the whole story. Sometimes there is also another influence, which is friction, which can come in many ways. For instance, the friction can come as air resistance to the movement of the pendulum. It can come as a friction here at the joint. You can take the whole thing, you can take the ceiling, the spring, the mass, and put it into a big bucket full of honey, let's say. And of course, there will be this friction happening. So the friction force also appears on the right-hand side with a minus sign, actually. It slows down things. This can be reasoned out, no problem there. And when you write it nicely, it becomes this equation. X second derivative, that's the acceleration, plus, and now here's the friction force, which has some constant of proportion d, and it depends on the velocity, plus omega square x, that's the acceleration coming, let's say, from the spring or from gravity, and this should be 0. Again, balance of forces. Here we go. Now this is called damp oscillations. And I'm going to look just at simple oscillations, not the exact pendulum equation. Otherwise, I would have to put sine of x here and things would become much more complicated. So I definitely do not want that. The last equation into our zoo comes like that. X second derivative plus dx first derivative plus omega square x is equal to ft. Ft is some outside force which is influencing my system. So for instance, I can take the pendulum, I can let it swing, and then I take a blow dryer and I start blowing air from one side. That's a force, a constant force in fact, which obviously will move the pendulum a little bit to the right. So if this blow dryer is really strong, we may have a pendulum which is moving like that. Or if you take a vacuum cleaner and start sucking the air, the pendulum from this movement can move to this side and just move over here. You are sucking really strongly, okay? So all kinds of things can happen. That's the right-hand side force. And this is called forced oscillations. And again, they can come in many situations. So let me just show one particular application, which is totally different from the ones that we have over here. I don't want to talk about springs, pendulums. I don't want to talk about material physics. I want to look at a totally different field, electricity, electrical circuits. There is something which is called RLC circuits. And I'm going to look at a serial circuit. So it goes like that. Usually you have some source, but I don't really care much about that at this moment. Then there is something which is called resistor. And resistor resists electricity, of course, resists current. And well, it's the strength of the resistance is called resistance, surprisingly enough. And it's actually denoted R, measured in ohms. something like that, some German name. Anyway, then you've got L, which stands for essentially for a spring, in fact. But this is not really a spring, or we do not perceive it as a spring, we see it as a coil. So we've got a wire, which is coiled like that, and this is traditionally denoted L, or the influence of it. This is called inductance, if I remember correctly my physics, and it's measured in, well, in Andries, I believe, something like that. Okay, finally, we are getting to this interesting place. This is capacitor, and the source actually must look differently. I think one of them is thick, the other one is long. It actually depends. The source may look also like that, with some mark denoted what kind of source it is. I don't want to go too much into it. This is capacitor. Its capacitance is denoted C, and it's measured in farads. So that's about it. Now, there is some current floating around, and you may ask, okay, what is this current? What kind of differential equation governs it? Because we want to talk about differential equations. And I talked to my friends from electrical theory, and they told me that the equation is actually fairly simple. You just take the second derivative of the current, and you add R over L, the first derivative, and then you add 1 over LC, the current, and this should be 0. So this is how it looks like if there is no source. Okay? So if you ignore this and you just connect it with a wire, you will get exactly this differential equation. Now you can look at this, call it D, you look at it and call it omega squared, and you get exactly damped oscillations, which is wonderful. If there is no resistance, then there is no damping, and you get harmonic oscillations. These things actually are studied in electrical theory, and they do lots of nice things about it. By the way, if there is no source, then of course one obvious situation is that there is no current either. It's simply a bunch of hardware lying around. And indeed, if you put 0 for the current, you will get a solution. So that's okay. Now you may ask, okay, is it possible to get some other type of a solution if there is no source of electrical power over here, like a battery or something? And the answer is, of course, because the capacitor actually can carry electrical charge, which brings us to the initial conditions. These are all differential equations of order 2, and with exception of the first one, they are all linear. And therefore, we expect to see 2 initial conditions. And that's exactly where some electrical energy can come into the play. It can come in the form of capacity over here, for instance. So that's the story about the electrical field. Before we move on, we can also add the source here, and then it appears as the right-hand side. And then it's forced oscillations. So you can see that these equations can actually serve many situations. Let's erase it. And now just let's have a look at it as mathematical problems. What can we see? Let's start by some technical things. So first of all, this omega constant will be always considered to be positive. It does not really make any change over here at this moment, but once we start solving, this will come handy. And secondly, there should be 2 initial conditions, and just to make our life easier, let's assume that we start at time 0. So the initial condition should specify position at time 0, some x naught, and the derivative at time 0, or perhaps I should have put it with dot. So derivative at time 0, which is the initial velocity. And that's a nice interpretation which works for essentially most applications of these equations. For instance, the pendulum, you move it to the side and you release it. That's the initial position, but you may release it and also impart some velocity to it. You may flip it up or flip it down when you are releasing it, and that's the V naught. Okay? So let's have a look at our equation. Let's start with the harmonic oscillation, because that's the easiest case. Of course, we know how to solve it because this is a linear differential equation of order 2. We have to find lambdas, so we substitute, well, essentially 1 here, lambda square here, get a new characteristic equation, we solve it, and we see that lambda is plus or minus omega I. And this is actually where it helps that omega is considered to be positive. You don't have to worry about things. It's very nice like that. And this obviously, because these roots are complex, this leads us to a general solution. And this general solution looks like this. Xt is some combination, let's say A cosine omega t plus B sine omega t. So that's a combination of a cosine wave and a sine wave. Now, there is a trick that one can replace A and B with a specific constant and a combination of sines and cosines, which then can be rearranged. This isn't really a problem. So in fact, this can be written as some capital A, which is the amplitude, times sine omega t plus some shift phi. So you simply take the graph of sine omega t, you shift it and you enlarge it by the amplitude A, and you get your result. So all solutions of a harmonic oscillation equation look like this. These are just shifted sines or shifted cosines. You can do the same with cosine, you just used a different shift. Okay? So if you prefer cosines, you can do A cosine omega t plus some different phi. No problem there. There are some equations which connect these constants. The amplitude is actually just square root of a square plus b square, for instance. Okay, so this can be done, not a big problem. This is extremely useful for people in electrical engineering because when they work with electrical circuits, this is what they really like to use. So the solutions are just sine waves or cosine waves, a very simple, straightforward situation. Maple can do it for us as well. Let's have a look at it. So here is the list of the differential equations that we are interested in. And at the end of the list, we also already fixed initial conditions, but they are all in general. I didn't assign any particular numbers. So these are general equations. For the forced oscillation, I'm actually looking at a very special case, but for the others, I'm actually doing the general things as we have them over here. So there is the harmonic equation as the first one, then there is the exact pendulum equation. That's ODEx for exact. Then there is ODED for damped. The other guys are exactly in this general form. And now I will ask Maple to solve the harmonic equation, just like that in general, and Maple can handle it, just like we did. Okay, no problem, a combination of sine and cosine. And if I also give Maple my initial conditions, then Maple can actually determine the constants A and B, or C1 and C2 as Maple has it, based on the initial values, which is very nice. So if somebody gives you a specific situation, you just substitute into the formula and you get your solution. So the harmonic notion is luxurious. This is a really nice mathematics, very simple case. That's why it is actually used a lot in applications in simplified situations, because we can handle it really well. The situation is more interesting when we get to the damped oscillations. What do we have there? Lambda. How much is lambda? Well, we know the score. We have to rewrite this as a second-degree polynomial and find the roots. So we just imagine that there is lambda square here, nothing here, and we find the roots. So we have to use minus d over 2, using the fact that the coefficient here is just 1. And then there is plus minus. We again divide by 2, square root of d squared minus 4 omega squared. And now the situation becomes really interesting. By the way, Maple can do this as well. Here we go. So these are the two lambdas in exponentials. We can see that easily. But what Maple cannot do, because it's just a computer, is to think. And when you look at this, you should start thinking, okay, there are actually several cases depending on how this square root works out. So there are 3 cases. One case is when this expression under the square root is actually positive. So what does it mean? Well, positive expression, d squared minus 4 omega squared greater than 0, this happens exactly if d is larger than 2 omega. Now remember, omega is some constant describing the forces in your experiment, and d is the damping. So this is a case when there is too much damping. So for instance, you take this mass of the spring and you suspend it in a really thick honey or something like that. So a lot of damping. This is called overdamped. Oscillations. And when you have those overdamped oscillations, it means that you get two roots, lambda 1 and lambda 2, which are real. And therefore, your solution is just a combination of one exponential, lambda 1t, plus second exponential, lambda 2t, as the argument. I should be writing, okay, let me be proper, and also over here. We should see a region of validity, of course. So, we've got beautiful real-valued solution based on exponentials. So that's the overdamped oscillations. Now let's have a look at second case. The second case is when the expression under the square root becomes negative. So d squared minus 4 omega squared negative, which is exactly when d is less than 2 omega. Because d is damping, this is a situation when we do not damp too much. Perhaps it's even 0, so there's no damping at all. So this is called underdamped oscillations. And then what typically happens is this. You look at this expression, you play with it a little bit, and you get lambda is equal to negative d over 2 plus or minus square root, and now I take this 2 and move it inside, and I get d squared over 4 minus omega squared. And now we know that this is actually a negative number, so we can keep playing with it. This is minus d over 2 plus minus square root omega squared minus d squared over 4, and this is a real number now, times I. This is typically called omega, let's say omega d. This is a special frequency. Omega is the original frequency of the system. If it's a harmonic oscillation, then omega shows you the frequency for the sine or cosine wave. So when you have harmonic oscillation, no friction, you can see pendulum moving at a specific frequency. Once you introduce damping, this frequency changes into a new frequency. And then there is this part, which is actually the real part of lambda, and this one comes to the exponential when we are forming the solution. So the solution looks like this. xt is equal to, I'm going to factor out this exponential, e to negative d over 2t, and then there is a part with cosine, a cosine omega dt, plus b times the sine part, sine omega t, omega dt. So we can see that there is oscillation, which is very similar to the one that we had before, but it has a different frequency. This frequency is now influenced by the damping, according to this formula. And then there is another part, the real part of lambda, which modifies this oscillation using an exponential function. Now, typically, d is also positive because it's damping. So let me put it here. d is positive. And therefore, this exponential has a negative coefficient in front of t, so it's an exponential which goes to 0. And this becomes an envelope for the oscillations. Okay? So if you want a picture, normally you would have oscillation like that. That's the harmonic motion over here. But because of damping, but a small damping, there will be a specific exponential which is pushing the oscillations down. So here's the exponential. And the original oscillation gets modified by this exponential. And the amplitude is getting smaller and smaller and smaller. So here the amplitude is constant, a harmonic motion. Here the amplitude is changing, going to 0. That's the difference between the case when there is no damping, harmonic motion without damping at all, and this case when there is a damping, but the damping is not too strong. If the damping becomes really strong, then you just get two exponentials combined, no oscillation happening. So this is a totally different thing. Once you start damping too much, you kill the oscillation. Now, of course, there is a third case when you have equality here. D is equal to 2 omega. This is called critical oscillation, or critical damping, or damping rather. I should be careful. So it's critical damping. It's a damped movement. When you have a critical damping, then this lambda is actually a root of multiplicity 2. This term becomes 0. Lambda 1 is equal to lambda 2 is equal to negative d over 2. And for that case, we know how things work. We have to introduce some linear term into the game, and the solution looks like this. It's at plus b times e to negative d over 2t. T from real numbers. So that's the third case. So you can see that when the situation becomes more interesting, when we introduce some damping into the system, then there is actually 3 different modes of behavior depending on how strongly we damp those oscillations. And we can reason it out, and we can also ask Maple to solve it not for a general case with d and omega, but for specific numbers. And we should get a specific solution which actually confirms to our expectations, hopefully. So here is a very specific setup where I chose some initial displacement. For initial velocity, I chose 0. We do not speed it up in any way. And I tried different values of d with the same omega. Omega, I think, was 2. In case you are curious, let me have a look. OK, so omega is 2, and therefore omega squared is 4. And initial velocity is 0. Now, the first case, when d is small, then it's exactly the critical damping, and then there is a strong damping. So I looked at those 3 examples, and I asked Maple to actually solve the corresponding differential equation, and then we look at a picture. Now, let's have a look at it. The gold curve, that's the underdamped oscillations, exactly as we expected. So there is an envelope, which is the exponential function. We can see it in the picture, actually, which is modifying the amplitude. And you can imagine that those oscillations will eventually go to 0. So that's the underdamped case. Overdamped oscillations, that's the red curve. And we can see that it's just a combination of exponentials. So it goes in a specific way. No big surprise there. Finally, the blue curve, that's exactly the critical damping, which behaves in a totally different way compared to these 2 guys. It's not just an exponential, but it's multiplied by a linear function. And surprisingly enough, it goes to 0 rather quickly, and then it levels off. So it behaves in a rather different way. Let me play with it a little bit. So I'm going to change the initial velocity to 10, which I interpret easily. I move the pendulum to the side, and before releasing it, or while releasing it, I still flick it upwards, so it goes even farther from the equilibrium before coming back. That's what I'm doing. With a spring, I pull it down, and when releasing it, I actually send it downwards also. So let's have a look what the solutions will be like. Well, we can see that this initial velocity moved the solutions upwards, even farther away from the equilibrium, and then they behave essentially in the same way as we expect them. So there is those disappearing harmonic oscillations and so on. Okay, 2 different motions. Let's try to change the orientation of the initial velocity. So I pull on the spring, and when releasing it, I move it upwards. So I'm actually adding energy to the spring energy. It's as if I was strengthening the influence of the spring going upwards. So I expect the spring to overshoot a lot also when going down. Well, we will see over here. Wow, that's quite a bit of overshooting. So we started on the top, and then it overshot downwards. And then the harmonic oscillations, the gold curve, actually, they go and settle down. The overdamped situation, you can see the red curve. So I moved the mass upwards when releasing it, but because it was suspended in honey, my energy wasn't enough to actually send the mass over the equilibrium point. You can see that the red curve stayed above the x-axis. I tried to move it, but this honey took too much resistance, so it just slowly oozed towards the equilibrium level. Okay? But the critical damping, when the damping is not all that strong, I was able actually to move the mass past the equilibrium point, and then it slowly got there. So yeah, it behaves exactly the way I expected using my common sense. Okay, Let's have a look at the last case, which is the forced oscillations. We know from theory that when we introduce some right-hand side, then we have to look at the general solution of the homogeneous equation, which is either the harmonic case or perhaps one of these three damped cases. And for my practical examples, I will actually just look at the harmonic case. And to this solution, we have to add something which is based on the right-hand side, which essentially preserves the behavior. And we also talked about the right-hand side sort of strengthening the behavior of the left-hand side if they are of the same nature. And that's why it's interesting that I actually used a special version where the right-hand side is just a sign of certain frequency. Now, it depends now all on this frequency. If this frequency is different from the frequency that we obtain here in the homogeneous solution, then this new influence is just added. But if the frequency of the right-hand side agrees with the frequency of the homogeneous solution, then there is this resonance thing happening and the signal increases. We talked about it when we were talking about linear differential equations. So let's have a look at it in practice. So again, over here, I prepared several cases. I have again the starting velocity 0 so that the situation is easy to read. And I tried different right-hand sides. C is the frequency of the signal on the right-hand side. There is a harmonic signal here, and I'm trying different frequencies. And let's see what the solutions look like for those frequencies. Okay, the black curve, which is thicker, that's the harmonic motion without any influence. So that's this equation, simple harmonic oscillation. Now let's have a look at the different situations. The gold curve, that's the case when I'm adding some forcing frequency, which is rather large. So how can I imagine this situation? Well, let's say that you have a pendulum. It's moving. So that's the harmonic motion. Let's forget about friction, okay? That's why it's simplified. So the black curve, that's a harmonic motion. The pendulum is moving without friction forever. But now I start really strongly breathing in and breathing out slower than the pendulum is moving. So when I'm breathing out, the pendulum moves to the right. When I'm breathing in, it moves to the left, if my sucking motion is really strong. And I keep doing that. So the pendulum should be moving to the right, to the left, to the right, to the left. Let's see whether we can see it in the picture, the gold curve. You can see that at the start, the golden curve is above the black curve. So we shifted the pendulum, the movement of pendulum to one side, but then the golden curve went down below the black curve, and then it went up again. So that's exactly the slow forcing frequency. We are influencing the pendulum in a slow, changing way. Then there is a blue curve. Blue curve means that we are looking at this pendulum, but we are breathing really fast because we have been running to get there. So as the pendulum is moving, our breath is making the movement erratic. It's trying to move, but we sort of influence it all the time, trying to make it move faster and slower with our really quick breath. So that's the blue curve, and you can see that it's sort of floating around the black curve. Sometimes it's above it, sometimes it's below, and it doesn't go in a nice smooth way. It goes up, down, because we are breathing really quickly. The red curve, that's the critical frequency. When we see the pendulum, and subconsciously, because of course we wouldn't do it intentionally, we wouldn't want to spoil it, but subconsciously we are actually synchronizing our moving with the pendulum. Well, what does happen? Well, you can imagine what happens. You don't need any physics for it, you don't need any mathematics for it, but you can see it here nicely. That's the red curve, and you can see how the amplitude is rather small at the start, but then it starts increasing and increasing and increasing and increasing. Crazily large amplitude, okay? So that's the resonance. And that's about these four cases, or rather these three cases, because those we are able to handle mathematically. We can do analysis of solutions, we can look at it nicely. Which brings us to the true pendulum equation. We cannot solve it analytically, and this was proved mathematically. There is no formula which would give you the solution, so we have to ask Maple for a numerical solution. Let's have a look at it. So, this is what you get when you ask Maple to solve the exact pendulum equation. Maple pretends that it gave you the solution, but this is the solution in the form of an equation. And you have to solve it to get your solution, and you cannot solve it analytically. So Maple did some work, but in the end, it was fairly useless. So let's have a look at numerical solutions. The blue curve, that's the pendulum equation as solved numerically by Maple. And the red curve, just for comparison, is the harmonic motion when we ignore the sine function in the equation. And when you look at it, you can see that actually these two are not exactly the same. Especially you can see the frequency is changing. So if you wait long enough, the red curve and the blue curve will be actually moving in opposite directions. So this is not very good, but this is caused by the fact that my initial condition was rather large. I started with x equal to 1, if I remember correctly. And 1, yes, 1. 1, this is in radians. So that's quite a lot. 1 radian, that's a big angle. Okay? So what I need to do, I need to change the initial displacement to something smaller. How about 0.3? Here we go. So if the initial displacement is rather small, then really the sine function and the x function do not change much, do not differ much, and you get a fairly good approximation. Now these two curves are quite close. Okay? So really when your pendulum is moving just a little bit, tiny bit, then these two equations can be both used without making a really big error. Okay? So that's a useful observation. Now, what I'm really curious about is how actually Maple got this numerical solution. How far can I trust it? That's a good question. Let's have a look at it. I can actually ask Maple to comment on the work that it's doing. So I'm going to run this code again. And before the picture, we have some interesting write-up. So let's see. Over here. We can see right here at the start that Maple decided to change the second order equation into a first order system of differential equations. Exactly our next topic in the theory of differential equations. So instead of solving this equation using some numerical method, it's actually looking at a system of first order equations, and then it applies standard procedure for solving first order equations. Here we go. The solution was found using RKF45 method. So it's using Runge-Kutta method of order 4 with Runge-Kutta method of order 5 as a control for making the error small. So this is really some heavy-duty machinery applied to a system. Just to review the stuff that we did in class, in lectures on systems, let's try to transform this equation into a system by hand so that we can see what Maple is actually doing. And then we can ask Maple to solve the system directly, without relying on the Maple doing the transformations. Perhaps Maple got it wrong. So it's better to ask Maple straightforward questions. Here we go. Let's review how we transform differential equations to systems. We want to reduce the order of the derivatives in the equation, and we do it using substitution. We take the derivative, and we give it a name. Now, in this particular case, when we imagine that x is a displacement, then there already is a name, namely its velocity. So that's the substitution which should reduce derivatives in our equations. Let's have a look at the exact equation. When I substitute for x dot, the velocity v, I get v dot, v derivative on the left, and then there will be omega squared sine x is equal to 0. And now I can take this equation, put them together, and I get a system. And the system reads x dot is equal to v dot is equal to minus omega squared sine of x. And we can see, I intentionally put v on the right farther there so that we can see the matrix of the system like that. It's a matrix where on the diagonal you have zeros, and on the second minor diagonal you can see these two terms. Okay, what happens if I apply this reduction to the harmonic equation? Well, I get v dot plus omega squared x is 0, and this leads to the following system. X dot is equal to v, and v dot is equal to negative omega squared x. Again, very nice 2x2 system. And in the same way, we look at the damped oscillations. I substitute and I get v dot plus dv plus omega square x is 0, and therefore I get a system which looks like this. X dot is equal to v, and v dot is equal to minus omega squared x minus dv. And finally, by doing exactly the same trick over here with the forced oscillations, we get a system x dot is equal to v, and v dot is equal to, and actually there's this damped oscillation part from the previous equation, so I can just copy this part, minus omega square x minus dv, but then there's also this ft part. So these are the system versions of my original equations. And here we set up the systems by ourselves manually. So for instance, for the differential equation without any effects, the harmonic oscillation, we can see a system which exactly corresponds to what we wrote over here. That's exactly this system. Then there is the damped oscillation, and it's this system. We can see this expression over here on the right in the second line. Then there is the exact equation, and we can see sine x, which is exactly this, multiplied by omega squared. That's the derivative of v. Yeah, that fits, and so on. There are some initial conditions also, just written in the special way for the system, because we know that this also works for the system. X naught is x naught. But now instead of the derivative, we simply put v. So we have this nice set of initial conditions for our systems. So we will now ask Maple to solve these systems numerically. What does it mean? Well, we take a look at such system, and we recall we had a short lecture on that. We can actually apply Runge-Kutta methods. For instance, the Euler forward formula, because we are provided with formulas for the slopes of tangent lines, with the slopes of solutions. So when I'm sitting at a place, and now I'm sitting in 2D, I have values for v and also for x. I can just substitute and get the slopes, and then I move for v and I move for x. Okay, no problem there. So I'm going to ask Maple for that. And in this picture, we can see a nice comparison. So for the harmonic motion, which is this equation without sign, we know the solution. This is the simplest case. That's the blue curve, dark blue curve. And the red curve is the outcome of the Euler forward formula applied to the system. And we can see that it does not quite work, and we know what to do. We have to decrease the step size. Or perhaps we have to switch to a better method. So I'm going to replace Euler method with RK4. And let's see, we got a perfect match. We are not really surprised. We know that RK4 method is very good for, let's say, run-of-the-mill problems. Unless there is some tricky part, RK4 will do really well. Now, what we have here is actually just the variable x, because we are interested in x, in the position of the pendulum. So I asked Maple to solve the system, but then I just looked at x. But in fact, we also have information about v, about velocity. So let's have a look at it. In this picture, we can see in blue the displacement, which means the angle for the pendulum, or if you want, it can be actually the displacement, the actual displacement. There is a simple transformation by a constant. Or it could be the position of the mass on the spring, easily. Now, the golden curve, that's the velocity. So you release the pendulum, and you can see that there is a certain displacement. That's the blue curve. And there's zero initial velocity, because that's how I set it up in my initial conditions. V naught is 0. And then I let the pendulum go, and after a while, the displacement will be 0, because it's right in the middle. That's exactly the intersection between the blue curve and the time axis. But all this energy that we had here, potential energy, got transformed into a kinetic energy, into movement. So you can see that the velocity is really large. But then the pendulum starts moving upwards, using the momentum, because it has a lot of momentum, it's moving fast. And as it goes upwards, then this momentum is getting exhausted. The velocity is bleeding out, feeding the potential energy. So the displacement is increasing and the velocity is decreasing until there is no velocity left. And that's exactly the moment when the golden curve intersects the t-axis and the displacement is at its largest. and then the pendulum goes back, and so on. So you can read this graph easily like that. So that's one possibility how to visualize the result of such a working with a system. But we had a video about different form of visualizing when we look at orbits. So we forget about time. We don't want to see time. We are just interested in the values of velocity and displacement. And that will be another picture. We can actually choose, let me show you. Over here, when I use the command, I have to say what I want to visualize. And we can only visualize two variables at the same time when we are at 2D. And we have three. We have time, displacement, velocity. So I did the solution twice. First, I asked the command to visualize time and displacement. And that's one picture. And I merged it with another picture, which is over here, where I asked the command to visualize time and velocity. So it's actually two graphs which are merged, overlapping. What I'm going to do here, I will ask the command to visualize velocity and displacement on the two axes. So the time will not be there at all, and that's what we call orbits. So let's have a look at it. This is the orbit for the pendulum. On the horizontal axis, we can see displacement, and on the vertical axis, we can see velocity. Now, we started with displacement 1 and velocity 0, so we started over here. Let me point it out over here. This is where we started. Now, as the pendulum moved, the displacement got closer to 0, which means we are moving left on the horizontal axis, but the velocity grew, so we are moving down on the vertical axis. That's exactly this type of movement that we can see over here. And the arrows, that's the vector field. We talked about it in that lecture on analyzing solutions of systems. Okay? So we are moving over here in time. And after a while, we end up at this point, which is where the velocity, that's the vertical direction, is the largest, and the displacement is the smallest because it's 0. And then the displacement moved to the other side until we got over here. So the movement of the pendulum is actually captured by a circular motion in this picture. We do not see how quickly we are going around. That's one of the disadvantages of the orbit idea. But we do see something interesting. For instance, physicists can look at this picture and interpret it in a way as a picture about the preservation of energy. The energy can be stored in position of the pendulum, how high you go, or in the velocity. And that's the horizontal and vertical axis, and we are sort of changing one energy to another. But we keep the energy. That's really nice. Okay, Maple can actually do animation. So let me just show you. This is the animation for our orbit. You can see how it goes around. So Maple actually simulated the movement and tracked it around at different time points. So that's something that we can do. Okay, let's add damping. So now we are going to ask for a damped system, which is this one, and compare it with the harmonic motion in the orbit picture. So the black curve, that's the harmonic motion without any damping. And the blue curve, that's the motion with damping. And if you can see the distance as an energy of the system, then you can see that the energy is being lost. You have a nice spiral because the friction is taking away the energy, and you have less and less of it, so you have less displacement, less velocity, less everything. And that's those nice oscillations which move towards 0. Okay? That's how they look like in the orbit picture. Okay, it's time to start with something really interesting. Here we go. Here we have two pictures. The picture down here shows the harmonic motion in red and the exact, precise pendulum equation in blue. That's the ideal. The blue curve, that's what we want. The red curve is what we get when we simplify our life. Instead of sine of x, we take just x. And we can see that from this picture, it doesn't seem that things would be really bad. But that's the tricky part, because in orbits, you do not see the time. You know that at a certain position in time, you are sitting somewhere on a curve, but you don't know when, at which place, until you investigate it. So these two curves, they look quite similar, but it may happen that they are moving on the blue curve through this lower part at a different time than in the red curve, and you don't recognize it from the orbit. So orbits are nice, but one should be aware that there are some limitations. Let's have a look at the top picture. This is just a picture for the displacement. So we do not see the velocity information here, but we can nicely see how the blue curve, which is the precise pendulum equation, does not quite work well with the red curve, which is the simplified harmonic motion. So for this particular situation, simplification did not work out all that well. You can see that the curves are very similar in shape, which is reflected in the orbits. Those orbits are really similar. But you can see that those two motions are passing through similar shapes at different times. So they are not interchangeable. Of course, we know that when we take small displacements, okay, we took initial displacement 1, so we moved the pendulum a lot. We know that then the simplification does not work well. So if I start with 0.3, now there should be a much better match. And you can see that there is, okay? So for small displacements, these two systems, they are actually providing reasonably similar answers. By the way, let me show you something. What happens if I move the pendulum a little bit, just a little bit, but when I'm letting it go, I flip it really strongly. I give it a lot of energy. What happens? Well, let me change the initial velocity to 4, I think, should be enough. Let me see. Yeah, it is, okay? So what you can see here is an interesting situation. Remember, on the top picture, we have the angle. And the harmonic motion thinks that we are still moving left and right. We can also see it here in the orbit. The harmonic motion is moving around and around and around. But the true pendulum equation noticed that we flipped the pendulum so strongly that we're actually going around in circles. So the angle keeps increasing. And the pendulum equation recognizes it, both in the orbit form and if we just look at the graph of theta, of the angle or displacement. Okay? So this is just a little curiosity. Okay, here we go. A little bonus. There is something interesting, an object, which works like that. You have a mass on a spring. This is the equilibrium position. And now you pull on it, but you also displace it to the side. And now you release it. So there will be two types of motions. One of them will be the swinging motion of the pendulum, but there also will be the bouncing motion of the spring. And these two motions will get combined. Now, typically in physics, we try to simplify our situation by handling, when you have such a mix, each type of movement separately. So you are looking at the swings, and you are looking at the bounces. Yeah, probably bounces would be the name for it. And in many situations, this actually works well. So let me show you mathematical simulation of this. Here we go. That's the system which governs the movement of a pendulum on a spring. This is called flexible pendulum in physics. And these equations are very difficult and they are not linear. For instance, in the first equation, you can see that the second derivative of r is equal to r times the second power, the square power of the angle. So this is not linear, definitely not. These are difficult equations, and therefore it's not really possible to separate the movements in general. But very often, as I said, it does work. Here we go. This will most likely take some time. On my home computer, this took several minutes. Okay, here we go. That was fast. So what we see here, the blue curve, if I remember correctly, is the angle. And the red curve, that's the displacement of the spring from the equilibrium point. So the angle goes left and right. You can see it in the picture. It goes left and right, left and right, left and right. And the bounces, they go up and down. And they seem to be working. OK, they are not regular anymore. Normally, if these two movements were independent, you would expect to see red curve to have the same amplitude all the time, the same tops, the same bottoms. And the same would go for the blue curve, which is the swings. But it's not true, so there is some influence between these two. As I said, those equations, they are sort of binding these two movements together, so there are some influences. But this is not unexpected. One would expect that there will be some things happening. I actually figured out by finding it on the internet to some extent. Okay, I got inspiration from people who are much better in Maple than I am. So I found a way to visualize it. Here we go. And as you can see, this mass, which is the circle, is moving left and right, swinging, but also going up and down. So that's the movement that we can see over here. Yeah, very nice. I sort of like it. For specific settings of the length of the rod, or rather spring, and the mass, things like that, stiffness of the spring, you can get very nice curves, especially if you dip the mass in ink and let it draw pictures. And you get really cute pictures for some combinations of mass and so on. So these movements can be really nice. I think we've had enough. Okay, a few more. So let me get ready for the next one. That's it. Sometimes it happens that for specific combination of parameters of settings, this flexible pendulum behaves in a totally unexpected way. Let me show you. I have one such combination here, so I have to set up the mass in a specific way. I have to set up the initial angle, and this. That should be enough, I think. Yeah? I got it right, I think. So we let it work, and this is a totally unexpected picture. When you look at it, the blue curve, that's the swings. And you can see that those swings are sometimes large and sometimes are almost disappearing. So the pendulum swings and then stops swinging, and swings and stops swinging, just by itself, no outside force. When you look at the red curve, that's the bounces. And you can see that they are actually going in sync with the swings. There is always energy somewhere in the system, but it is changing. You see energy in swings and almost no bouncing. And then you see a huge bouncing, but also almost no swings. So the system is capable of sort of directing the energy to one of these two movements and changing it without any outside influence. It's built into the system. So it's a very complicated system if it's capable of that. Let me look at the simulation. And again, we'll have to wait a little bit for that to get... Oh, that was fast. Okay. And this is how it looks like. So we've got those bounces, and then suddenly they become swings. And then they become bounces. Now, you may say, okay, this is just a mathematical model. How about the reality? And the answer is, well, it takes a lot of care because you have to set up all the things just right. But yes, this has been confirmed experimentally in a lab. So this can really happen. Actually, it does happen inadvertently sometimes, because when I was at high school, we actually had labs in physics where we had to work with spring, mass on the spring, and we had to measure the stiffness of the spring based on the frequency of the swinging, things like that. And sometimes people would have this spring swinging left and right, and the teacher would say, oh, you moron, you have to pull it down, you have to pull it down. We are not supposed to, swing it. But perhaps the student was actually innocent, because as we can see, this situation started by pulling the string almost horizontal, almost vertically. It was pulled down and displaced by just a tiny, tiny amount. So it's easy really to make a tiny mistake, but this system is capable of taking this tiny initial swing and changing it to big swings. So yeah, this is very nice. So that's it regarding springs and pendulums and things like that. I think this is a very nice application of differential equations to physics. And we got actually to review some interesting notions about analysis, visualization, and so on. So that's it for this example. Let's move to the next one. For our second interesting example of applications of differential equations, we will look at virus propagation, or if you want to put it another way, disease simulation. Now, I've been talking about this for years, and I actually quite enjoyed it, and we had good fun with students. Then the COVID came, which took some fun out of it, but hopefully this is all behind us, and we can have fun with this example again. So let's have a look at it. We have some population of people, and we have some disease, and some people are infected. So IT, that will be how many people are infected. Now, to take into account that you have populations of different sizes and so on, it's actually better to see this as a proportion. So these are infected people, proportion. So this number is taken from the range 0, 1. If I is equal to 1, then everybody is infected. Now, apart from infected people, you have to have also some people who are susceptible Let me check. Yeah, I think that's the right one. Again, this is a proportion. And these are people who are not infected yet, they are not sick yet, they are healthy, and they are capable of contracting the disease. Okay? Now, the simplest model that you can think of is exactly based on these two groups. It's called SIS model. How does it work? You are healthy, you meet somebody who is infected, you contract it with some probability, you get sick, you are sick for a while, then you get healthy again, and you can again join the game. So from infected, you again become susceptible. Typical example is the common running nose, common cold, I think they call it, whatever, okay? Annoying, but yeah, you can live with that. So SIS model, how does it work mathematically? We will start with the infected people. So the derivative. How does the group of infected people change? Well, it gets larger if somebody who is infected meets somebody who is susceptible and successfully transmits the disease. Now, for that, we have to go to people from probability statistics, and they tell us that when you have proportions of people, and that's the advantage of having proportions. If you have proportions of some groups and you multiply them, then you essentially get the probability that they meet within a specific time interval. So I multiply I by S to essentially show the chances of their meeting, and I multiply it by some constant beta, which fixes the probability to be exactly the right number, and also includes information about the disease. How contagious is it? Because every time infected person meets susceptible, it's not quite sure that there will be a successful transmission. It depends on many factors, and one of them is, let's say, the danger, how dangerous the disease is, how quickly it jumps from one person to another. Okay, so we've got increasing numbers of infected people, but after a while they get healthy again and they leave this group. Now, this is actually tricky. Because, for instance, when you take common cold, when you contract it, when you get it, it usually lasts about 3 to 7 days, and then you get healthy again. So there is a time interval involved, but this is impossible to capture in the form of a differential equation. So we do something else, which is not exactly the same, but okay. We will say that a proportion of infected people gets healthy again. Actually, I should use gamma here. Okay, that's the traditional constant. There are some traditions for denoting different factors in the medical field, so I will try to follow them. So gamma is the constant which describes how readily infected people get healthy, which means that they become susceptible again. That's the SIS circle. Okay, that's the equation for the changes of the infected people. Now we look at the susceptible group. Now, because there are just two groups, it's quite obvious that every time somebody moves from one group to another, it influences both of them in the same way. So here we see people moving from S to I, and therefore they are actually leaving the group S. And these are people who are moving from group I to group S, so they are enlarging the group S. And that's it. This is the system of differential equations for the SIS model. Okay, before we look at some picture, let's talk about it. First of all, I can see I times S, product of two unknown functions. This is not a linear system, unfortunately. Otherwise, the situation would be much easier. It's not a linear system, but we are used to the fact that interesting systems are not linear. That's life. What can we say about them? Well, we had this video about analyzing systems. Let's ask some good questions. For instance, are there any stationary solutions? Good question. Well, could it happen that the derivative of I is equal to 0? And because they are essentially the same, those derivatives, just with opposite signs, this is actually enough to also figure out that the derivative of S is 0. Well, I look at this formula, and I can notice that I can factor out I. So I'm really asking, I times beta S minus gamma, could it be 0? And I also notice that there is no t in the equation, so it's autonomous system, which is wonderful. Okay, are there any values of I or S that would make this left-hand side 0 regardless of time? Definitely. One possibility is when I is equal to 0, and then, of course, S is equal to 1. How do I know? Because these are the only two groups. So S plus I must be 1. Well, you have a population and nobody is infected. Well, then nobody gets infected in the future either. That's a stationary situation. Wonderful. Okay, we can see another possibility. When S is equal to, and let me think about it, in order for this to be 0, S has to be gamma divided by beta. And this number is not 0. So this is an interesting situation, and it's not 1 perhaps either. We have to be careful. For some settings, this is not possible. We have to make sure if this number belongs to 0, 1. Then we have this special stationary solution. And then, of course, for I, we get the complement to 1. 1 minus gamma over beta. So there are actually two stationary solutions. One of them is obvious, and the other one is not obvious, but yeah, it seems that there is a balance where in this mechanism of people moving from one group to another, these two streams of people, there is one stream going one direction, another stream going the other direction. There is a specific situation where those two streams are the same, and then those two groups, they become stable. Okay? Now, we could inquire about stability of these two equilibria. And this takes some work. We could, for instance, look at these expressions and ask what happens if I am near this stationary situation and I shift a little bit away. How does this derivative look like? Does it bring me back or not? Things like that are possible. Let me just tell you that this one is unstable. So when you have a community and you introduce some infected people in it, there is a low probability that you will get back. It depends on those parameters, beta and gamma, but typically this is unstable. So let me just put it, okay, in the brackets like that. Typically unstable. Okay, let's have a look at some pictures. So this is a system of differential equation for SIS model, and when I look at it, beta SI minus gamma I. I couldn't use I. Okay, so don't get distracted by IN here. IN is infected. If I used I, Maple would think that this is a complex unit, a constant. Okay, I had to be careful. Gamma, gamma, beta, yeah, everything works well. So let's have a look at some results. Here we go. I chose some constants which I found in some medical journals. So they are, okay, they are not constants of some particle disease, but I sort of put them so that they are nice numbers, but reasonable, close to some real-life diseases. And what we see here, again, we have to be careful. We have three quantities now: time, the number of infected people, the number of susceptible people. And we can only choose two quantities to show at the same picture. So we have time on the horizontal axis, and on the vertical axis, I can see the number of infected people. So in this particular scenario, I started with 20% of infected people, and after a while, the situation stabilized at about 70% of infected people. By the way, if you try to play with it, you will find that this stationary solution is stable, typically. So this is a nice typical picture for a stable situation. Let's have a look at another picture, the same settings, the same beta and gamma. And now we can see actually two graphs merged. One graph is the number of infected people in red. The blue curve, that's the number of susceptible people, which essentially means healthy people. And we can see that together they should give 1, and when you look at the numbers they do, it's a nice stable situation. How does it look like if I look at the orbit? And the answer is, it looks like this, and the arrows are actually quite useful because you can, it helps you to read the orbit. If I didn't put the arrows there, it would be difficult to interpret. Let's have a look at the initial conditions. I have them somewhere here. So the initial conditions are that the number of susceptible people is 0.8, so 80% of people are healthy, and 20% of people are infected. And you can see it over here. We start at 0.2 proportion of infected. Now let's find it in the orbit picture. Let me run it again. So on the horizontal axis, we can see the number of susceptibles. Vertical axis, the number of infected. And at the starting point, we have 20% infected, 80% susceptible. That's this position. Okay, so at this point, we are at time 0, And the arrows suggest that we move in direction to the upper left corner. So as the time goes, the proportion changes in this way. So the number of susceptible people is getting smaller, and number of infected people is getting larger. And it is a straight line because these two quantities add up to 1. So it must be a straight line. And now here is the location which was actually the limit. That was the stabilized situation. So in a limit, we would get here in the orbit and just stay there. So we can see that there is a vertical line over here at which opposite arrows meet. So these are possible situations where different initial conditions stabilize. Now, this is actually interesting. The fact that s plus I is equal to 1 means that the starting positions can be only along this oblique straight line, connecting number 1 here and number 1 here. So on this straight line, we can have the only permissible starting conditions. And when you look at it, you can see that no matter where you start on this line, the arrows will always move you towards this point. So all initial conditions eventually end up here, and that's most likely this stationary solution. I would say that it's stable based on the picture that I see. Now, there are also some other pictures, but unfortunately, they are just pictures for differential equations without taking into account that s plus I must give 1. Okay? So these are not realistic. These are like mathematical virtual realities which are not connected to our situation. Now, I mentioned that the behavior of the system depends on the constant beta and gamma. And as it turns out, and you can see it over here in the picture, they are not really important as such, but the ratio is important. So I'm going to keep gamma and change beta a little bit. Now remember, beta is the probability that when two people meet, they will transmit the disease. So beta in this picture, in this experiment that I have, is 0.5, and gamma is 0.15. So the chances of transmission are higher than the chances of getting healthy again, in a way. That's interpretation. Let me try to change beta to 0.15, and let's see how it changes the dynamics of the disease. So now the probability of getting healthy is much strengthened compared to probability of contracting the disease. And let's see how this whole vector field changes. And it changes totally, because now all the arrows are going down towards the lower corner. And remember, we are only allowed to be on this oblique line. So no matter where we start on this oblique line, which starts at 1 and goes all the way down to 1, no matter where we start, our orbit will keep going in this direction to the lower right corner, and it stays there. So this suggests that it's actually impossible for this community to keep some disease in it, disease of this type. So if the transmitting power of the disease is lower, then the community, even if somebody brings it there, defeats this disease, which is wonderful. That's what we want. Let's have a look at this. Notice that if beta is the same as gamma, then S is equal to 1. That's the other stationary solution, but it's actually the same as the first one. So there is just one stationary solution when everybody is healthy. No other stationary solution in the game. And it's reflected in this vector field. We can see it over here. And this brings one to an interesting question. Can we somehow help society so that it works like that with all diseases? Which brings us to inoculation. Inoculation simply makes it sure that this is the picture for the disease that we fear really a lot. Okay? We'll talk about it a little bit later. So that's the SIS model. Let's have a look at our second model. It's called SIR. Again, these are three groups, proportions that add up to 1. And the R group, these are people who do not want to play the game anymore. These are so-called removed. And as I said, this is going to be a proportion. Now, it's not just about groups, but also about how people move from one group to another. For the SIS model, we can see a merry-go-round. You've got group S, group I, and people move both ways. In the SIR model, SIR, the situation is somewhat different. You've got people in susceptible group, and they move to the infected group, and these move just to the removed group. There is no going back to S from R in this model. That's the end. So there's just one directional flow of people. How does it go? Well, the infected people, they are gaining new members of the club by meeting susceptible people with some probability of transmission. And they are losing members at a specific rate. Again, it would be better to somehow incorporate time constant, but that's not possible. Now, it's traditional for the SIR model to use a different letter here. Let's call it nu. This is, let's say, less popular. Everybody knows gamma. Nu, okay, that's a letter, another Greek letter. How about susceptible people? Now, they are just losing members. They are losing them to the infected group. And they are not gaining any new members, while the last group, removed, keeps gaining new members from the infected group. So that's the system. And you look at these three equations and you ask, are there any stationary solution? And the last equation tells you right away that there's only one possible stationary solution. And that is when the number of infected people is 0. And at that moment, all these derivatives become 0. And then you do not really care about the number of susceptible and removed people in the population. By the way, removed people, how do you become removed? How do you say, I don't want to play the game anymore? Well, essentially two possible ways. One of them is that you get the disease and you become immune after you get healthy. And when you are immune, you are not susceptible at all. The other way is that you get the disease and you die. And then you cannot get it again, so you are removed from the game. When we talked about proportions, in order for the mathematics to work well, we are not allowed to change the population size in the middle of the experiment. So we have to keep the population size stable, and when somebody dies, we simply move them into this special group. Now, for the purposes of the model, it's actually the same thing if you die or if you get healthy again and get immunity. These are the same things, the model doesn't care, which is sort of curious because we usually do, but that's mathematics for you. Okay, just one stationary solution. Is it stable? I don't think so. We will see. Once you introduce some infected people, again, it depends on the constants. You may want the diseases to die out again, so you want this to be stable, but typically for many diseases, this is not true. Okay, so that's another thing to talk about. Now, before we look at pictures, there are 3 unknown functions plus time, which makes 4 quantities that we may want to see. One possibility is to make a separate graph for each function, as it depends on time, and perhaps overlay these 3 graphs. This could tell us something. Or we can choose any pair of functions and show an orbit for them. Let me start with this orbit business. So over here, I set up the system for my SIR model. And now for some constants, again, these are reasonably truthful constant or reasonably realistic. What we can see over here is the orbit. On the horizontal axis, we can see the number of susceptible people. And on the vertical axis, we can see the number of infected people. So where do we read it? How do we read it? At the start, 99% of people were susceptible. So the whole population was healthy. And there was 0.01% of people infected. So it's just like you have population of 10,000, which is a huge city, and one infected person comes in. Nobody was immune or dead at the start. Okay? So the starting point is over here. Almost everybody is susceptible, nobody is infected. And as the time goes, the number of infected people was going up and the number of healthy people was going down. And it was kept going down all the time. So the number of healthy people was steadily decreasing. But also here, the number of infected people is decreasing. So at the end, it seems that everybody moved to the group R, removed. And let's hope that these are all guys who are healthy and they get immunity. That's the ideal situation, ideal outcome. Okay, here we go. 3 graphs. Here we can see them. The blue curve, that's the number of susceptible people. The red curve, that's the number of infected people. And we can see how the number of infected people shoots up and then goes down in time. And everybody moves to the black curve, which is the removed people. So we sort of guessed it right. And let's face it, you would guess this even without knowing any mathematics. If somebody told you, okay, this is the mechanics. People are healthy, then they get sick, then they get healthy again, and they have immunity. So what will be the development? Well, you would guess something like that. So this is not really surprising. Let's use this opportunity to review a little bit about numerical mathematics. How does it work for the Runge-Kutta methods. We are essentially working with 3 graphs at the same time. Here we have time, and here we have infected people, susceptible people, removed people. We start with some initial data. Nobody is removed, almost everybody is susceptible, and there is few infected people. We split the time axis into chunks of equal size to make our life easier. So there is a step size h. And now notice that we know at time 0 the values of r, s, and I. We can substitute them here, and when we substitute them here, we get the slopes. And when we know the slope and the position, we can do the tangent line. So we form tangent lines, and for the slope, we use exactly this formula. So this will be the initial value plus the derivative times h. And the derivative we substitute from here. And similar formula works for all the other guys. Initial value plus the derivative times h, and so on. And you move simultaneously all of them, because you have the initial data, so you can substitute, change all of them, get to a new place. And once you get to the new place, you can again take this information, substitute to the right-hand side, you get the slopes, and you can make simultaneously the next step. And you keep going like that until you get to the end. Okay? So that would be the Runge-Kutta approach. And if you decide to do it in an easy way, this is actually the Euler forward formula. I may try to do more journeys and try to find some balance, Runge-Kutta order 2, 3, 4, and you can play with it a little bit. Once you have a formula for the slopes, you are in business, of course, for all Runge-Kutta methods. So let's try just something simple, and I'm not going to call on any procedure. I just program it manually. Little implementation of the Euler method for this situation. So I chose the horizontal step size to be 10, and I will be interested in time horizon 100, let's say, seconds, whatever. And there are some initial conditions which I borrowed from the previous example, from the one that we can see on the top. And now there is a simple code which starts at the initial value, which is the previous one, at time k minus 1. Then it substitutes into the formula for the derivative of infected people. And when we compare it, we can see beta, we can see s times I, which is this, and we are subtracting constant times I. Yeah, so these are exactly these formulas, and they are multiplied by horizontal step size. So I really just took these formulas, substituted for derivative, and programmed them like that. And I make a loop, and then I just visualize the outcome. Here we go. Well, is it? Well, negative number of susceptible people, this does not quite sound good. So this is obviously not very good, but the general shapes are okay. But that's because I used a really huge step size. You can see it here, those segments on time axis, they are really huge. So let's try something more reasonable. Let's say step size 1. That sounds good. Wow. Now let's compare it with the picture here. Yeah, we are essentially there. So these Runge-Kutta methods, they really work. And it wasn't difficult. I just programmed a few lines of code. Okay? So that's very, very nice. By the way, our motivation is to make this group R as large as possible so that the infection doesn't have any room to play. You can become a member of group R by getting sick, then getting healthy, and having immunity, by dying, or by getting vaccinated. If the vaccine is safe, and if it works, that's the best way to become the member of group R. And essentially, using this model, you can figure out the constants beta, mu, and so on. This can be obtained from data on people. How many people are sick at different times, how many people are healthy, and so on. You look at the dynamics, and you can actually get estimates of these constants. And based on these constants, you can figure out how many people in population, again, we talk about proportion, how many people have to be vaccinated so that if disease comes, it dies out on its own. You remember the picture when all the diseases went to 0? All the cases? Well, that's exactly what we want to do. Now, depending on how the disease is contagious, this proportion of people that need to be vaccinated can be rather small or rather high. So there are some diseases for which if you vaccinate like 60, 70% of people, then this disease can come from outside and then it dies on its own. And you're fine. For some diseases, they are so bad that you need to vaccinate something like 95% of people if you want to be sure that if the disease comes from outer space, it will die out on its own. Okay? So these are really interesting things. Of course, it's assuming that this vaccination is actually a vaccination. Typically, when you say vaccination, you mean something which you get, and then for the rest of your life, you are safe. So there are vaccinations like that, and for those, these models really work well. Okay, we need one more example over here. This is SIRS model, which essentially, again, if I draw pictures, draw arrows, you are susceptible, you get the disease, you become removed by getting immunity and surviving the disease, and then after a while, this immunity wanes and you become susceptible again. Let's see. Now, if you understand how these previous equations came about, this should be easy. Let's see. Infected people. They are gaining new membership from the susceptible people, and they're losing membership to the removed group at a specific rate, omega. The susceptible people, they're losing membership to the infected group, and they're gaining new members, constant gamma, from the removed group. And finally, the removed group is gaining new membership from the infected people and losing numbers to the susceptible group at a rate which is proportional to how many people are removed yet. So this is a new model. Let's just quickly look at some illustrative pictures. And again, these pictures are what one would expect. So it seems that for at least some interesting combinations of parameters, again, the situations tend to stabilize. We can see here all three curves in one picture. The number of infected people shoots up, that's the red curve. The black curve, the number of removed people. And it seems that in this particular situation, it's also possible for a part of population to survive, even though they do not have immunity and they were never sick. So all kinds of situations can happen. These models can be used to, let's say, predict what will happen, to influence our actions. They have one big problem, they are simplified. And we actually talked about it over here. In many cases, the transfer between different groups is not based on probability, but on time interval. So for instance, immunity lasts half a year and then you lose it. You are infected for 2 weeks and then you get healthy. And this actually requires a different approach to model accurately. And if you are using these models, you shouldn't trust them all that much. You should be aware of the fact that they are not all that faithful. There are models which are better, which take into account this time interval problem, but they are done in a totally different way. Agent models, things like that, discrete models, much more work, totally different part of mathematics. Before we go, the difference between these models can be actually very important, for instance, for zombie apocalypse. Traditional point of view at zombies is through the SIR model, which means you are healthy, you get bitten by zombies, you become a zombie, and then you have to be removed, otherwise you are around forever. So this is the traditional approach, but there are some books, some movies, which actually look at it as a SIRS model, because they assume that if you are a zombie, you can actually become healthy again. The removed may mean that you are somehow healed. So these are interesting things. They are much more complicated models with M group and so on. A lot of fun, but we are out of time essentially. Let's move to something totally different, a third example. For our third and last example, we will look at population dynamics. Now, we already visited this topic once before when we are looking at applications of first-order differential equations. And we will need some of that knowledge here. But now we also know how to handle systems of differential equations. We know how to handle situations with more variables and therefore with more populations at the same time. So imagine some resource, ecological resource, let's say a wheat field, and there are two different populations there, two different species, let's say mice and prairie dogs. Now they are both interested in the same resource, in the wheat. So let's describe their interaction. And we will start with the logistic growth model. So we have population number 1, which has n1 members. And this population multiplies with a breeding constant R1. That's how they would breed if they had infinite resources. But they also have some capacity for their population, which is essentially based on their viewpoint of this resource. So those mice, they look at the field, and they essentially see how many mice it can support. But then there's the second population, the prairie dogs, and they also have their multiplicative constant. And when they look at the field, they may see a different capacity, carrying capacity, they call it. So these are two different viewpoints, and now let's put together some equations. So the population N1 changes. How? Well, proportionally to its number. So there is the breeding constant divided by K1 times the size of the population. And now there is the second term, which is slowing down the growth, essentially. So we take the capacity as the first species sees the wheat field. And this is reduced by the number of population, but also by the second population. However, this second population is eating up resources at a different rate, because a prairie dog is larger than a mouse, so a single prairie dog eats more than a single mouse. So there is some constant here describing the ratio between those two, let's say, demands on the environment. For the second population, it will be exactly the same story. So R2 over K2 and 2, that's the usual breeding, exponential breeding, but now the stopping part. K2 minus N2, this is how much capacity is left when the population N2 has a specific size, but also population N1 is taking away, and there is some constant beta 21. Now, one would expect that these two constants would somehow be related, because they're both speaking about requirements of these two species, about relative requirements. Let's not worry about that. These two differential equations, it's a system of first-order differential equations, which is not linear, because we are multiplying here the unknowns. This is called Lotka-Volterra competitive model. And this competition is peaceful. They are not eating each other or killing each other. They're just trying to out-eat each other, so to speak. Let's have a look at the system. We usually worry about stationary solutions. So let's ask about stationary solutions. Well. One of them is quite obvious. I want to make the derivatives 0 by choosing n in a specific way so that the right-hand side is always 0. Now, always here is easy because, again, these are autonomous equations. The time variable does not make any appearance here. So this is really easy. How do I make the derivative of n1 equal to 0? By taking n1 equal to 0. That's an obvious choice. What happens here? Then n1 is gone, and we can also put n2 being 0, and we have a stationary solution. Yeah, that looks good. n1 0, n2 0. But we can also keep n1 equal to 0, and for n2, we can actually choose the full capacity. n2 is equal to k2. So the field is simply filled with prairie dogs up to its capacity. Of course, quite logically, we can expect a symmetric situation when for n1 we put k1, and for n2 we put 0. Is that true? When n2 is 0, then this derivative is 0, then this term is gone, and n1 equal to k1 will make this derivative 0. Yeah, it works. So there are three, let's say, obvious stationary situations, and then there is a fourth one. Can we make these two factors equal to 0? And the answer is yes, because these are just linear equations, two linear equations. So definitely n1 and n2 can be found so that, and let's say that I write it like that. n1 plus beta 1, 2, and 2 is k1, and n N2. Okay, let me write it this way. Beta 2, 1, N1 plus N2 is equal to K2. So these are two linear equations. And now a lot depends on this matrix that we can see here. 1, 1 on the diagonal, betas on the other parts, on the other places. Typically, there would be just one solution, just one stationary solution. But sometimes it may happen, for instance, if you've got two competing populations that have the same demand, then those betas will be just one, and you will have essentially just one equation, and then there is infinitely many solutions. It's a straight line of stationary solutions. Analyzing stability is not all that easy. Let's not worry about it too much. Let's just play with it, and we will see what it yields. So, here we go. We are going to read the equations, and hopefully, yeah, they look the same. They look the same. And now I chose some parameters, and just out of curiosity, these two populations multiply at the same rate, and betas are 1, and they have also the same viewpoint of the capacity. So these are essentially two equal populations. Let's have a look at it. That's how the slope field looks like. And when we look at it, we can see that there are many possible starting points for the sizes of our population. And depending where we start, the populations will move towards a certain place. And there are places where those populations meet, which is this. It looks like a straight line to my eye. So that would be exactly this line given by this equation. Remember, in this particular case, k's are the same, r's are the same, betas are 1. So this is really just n1 plus n2 is equal to k. Just one equation. That's the stationary solutions there on the line. I prepared a picture where I actually looked at several situations. Here we can see it. So those circles, these are positions for the orbits given by initial conditions. So on the horizontal axis, we can see the population size for n1. On the vertical axis, population for n2. And for instance, this circle, which is right here down at the lower edge, how do I read it? Well, the population n1 is sort of middleish, but the population n2 is very small. So there are lots of animals of population n1, very few of population n2. And then as the time goes, we are moving towards to the right and up. So both populations are increasing in size, but the population n1 is increasing much more. It doubled. And the population n2 essentially also doubled. So they're increasing at a similar rate, at the same rate essentially, until they reached a point over here. And we can see that this point where they stayed is close to this position where the arrows go against each other. So that would be the stationary point given by this equation. And also here, the population started large, and then it went smaller and smaller, too many animals, until they stopped at the place where the arrows meet. And the same here. So that would be the line of stationary solutions. And it seems that it doesn't really matter where we start. So we can have many animals, small animals, or we can have many animals of one kind and few animals of the other kind, for instance here in this area. And we would still go towards one of these stationary points. But none of them is obviously stable, because if we move a little bit away, we end up at a different place. Okay, let me just show it. So here is this line. Each point here is a stationary solution of this sort. So I'm sitting here at my stationary solution, feeling really great, but then some outside force, let's say, drops in by parachute few animals of one kind, but only of one kind. So it moves me in direction, let's say, of population n1. Population n1 increases. Now I'm sitting now here, and what happens? According to the vector field, the situation will be moving in this direction, and I end up here. So I end up at a different stationary point. That's why this one is not stable. Okay? So now we see actually, based on this example, that these stationary points most likely are not stable. Okay, let me show one possible situation. So here we have two populations. The blue one is rather small, the green one is a little bit larger, and both of them increase in time. So I think that this corresponds exactly to this case down here in the slope field. That's the orbit, the blue orbit that we can see in the orbit picture. Now we can see it as a graph of those two populations. Okay? Let's experiment a little bit with our picture. So those betas are the same, which means that those two populations, they are essentially eating about equally. Each animal in each group eats equally of the wheat. So let's increase the consumption in group 1, let's say. Actually, beta 1, 2 over here. That's for group 2. So we're increasing the consumption for group 2. And let's have a look at the change. And that's really surprising. It seems that no matter where we start, we end up with the population N2 having the capacity K2, and the population N1 will die out. This is pitiful, but yeah, the arrows suggest exactly this picture. There is no way around it. So it seems that for such a case, when the population N2 eats really a lot, it's able to starve out the population N1, and this solution seems stable now, because all these solutions go to there. We see the orbits, so we have to imagine that we are moving at time along these curves. We start at a circle and we move. The starting points are exactly the same as before, but now I just changed one constant. Well, logically, if I change this constant in the opposite direction, so if I let this population eat less, I would expect the opposite outcome. Yeah, exactly. So now the population N2 dies out, the population N1 survives. So these are really interesting things. One can play with them. Yeah, this population dynamics, it's fun. It's even more fun if you introduce the ability of one population to eat the other. So let's have a look at it. Let's start with something really, really simple. So there are two populations, and now I have a little trouble how to call them. This is called predator-prey models, and both of them start with P. So I'm going to use P for predator, and I'm going to use F for prey, because it's essentially acting as food. Okay? Now let's have a look at the mathematical model, at possible mathematical model describing the interaction of these two groups. So let's start with food. Here we will make situation easy on ourselves by just looking at the exponential growth. So let's assume that this food population, if we left it alone, would just multiply using the exponential growth with constant r. But the predator population drops in, and sometimes they meet. And the frequency or the probability of their meeting is f times p. We talked about it before. Then there is some constant which is fixing it so that it's really a probability. And then there is some constant which actually describes the success of the predator when they meet prey to actually make a kill. Because this is not always true. Not always when a predator and prey meet, it results in something catastrophic. So there will be some constant, typically beta. That's for the food group, for the food population. How about the predators? Well, the predators, they like to multiply, but their ability to multiply depends on the supply of food. If there's less food, they multiply less, and so on. So this is typically done like this. If I copy this group, I will find out how much food this predator group has, and then I add another constant, which takes into account this breeding success and things like that. And then this population also dies at a certain rate, let's say mu p. So that's a system, and again, this system is not linear because we are multiplying the unknown functions. We could again try to work out some stationary solutions. For instance, when f is 0, when there's no food, then the predators die out. Okay, so the trivial solution 0, 0 for both groups, that's definitely a stationary situation. Good question, are there other situations one could play with it? Let's have a look at pictures. So, here we go. Here we have the equations, and I hope I put it correctly. Yes, I did. The constants, they agree. And let's have a look at a specific situation. This is the vector field, and when we look at the arrows, they seem to be going in circles. So the orbits will be something like ovals or something like that. So this tells me that the solution is most likely periodic. And let's have a look at some case over here. Now, when I look at it, let me see. The blue color, that's the prey population or the food population. So at the start, there is just few of the food, let's say few rabbits, okay? Just very few rabbits. So the predators who are depending on the rabbits, which could be, for instance, people, are dying out of hunger because they have no rabbits to eat. And once the population of predators goes down, the rabbit population shoots up because nobody is eating them. And once there is lots and lots of rabbits, the predator population starts meeting them a lot and catching them a lot, eating a lot, and starts multiplying. And then there is a lot of predators, so there is this hill, this green hill, and a lot of predators means a lot of dead rabbits, so the rabbits go down in population and so on. This is periodic, it seems. So that's the model, which is called Lotka-Volterra. Predator-prey model. Let me extend time so that we can appreciate better whether it's periodic or not. Here we go. Yeah, this seems to be periodic. It's actually possible to prove that this is periodic. Let's have a look at the orbits. Okay, what do we see here? We started at 4 different initial conditions, different starting points for our exploration. Now, they are all in the same horizontal line, so which means that the predator population was the same in all 4 experiments. We were just changing the prey population, the size of it. On the left, we can see a situation when there is just very few of the prey population, or perhaps a little bit more of them. Now, how does it work? We start as a specific situation, and it seems that there is just a few predators. Because there is just a few predators, the prey population grows. So we are down and moving to the right. That's the growth of the prey population. When there is a lot of food, the number of predators goes up. So we have to go up vertically. And as the number of the predators is going up, they are eating more of the prey, so the number of prey is getting smaller, and we are moving to the left. The horizontal axis, that's the size of the prey population. So when it's getting smaller, we have to be moving to the left. And as we move to the left, there is just a few of the prey population, and the predators, they start dying of hunger. And so they go down in population, which means downwards, okay? So again, this cycle shows sort of like transformation of energy, like we saw it with the pendulum. Well, it's not exactly precise, but it sends a similar message. Okay, this is actually fairly interesting, and it seems that we are really getting back to where we started. So this situation seems to be periodic. Now, when I see these pictures, I'm wondering, especially the previous one, let me show it again in the original form, I am wondering about those stationary points. I'm just thinking, okay, could it work? Let's have a look at it. So the first derivative for food is f times r minus beta p. Now, I want this to be 0 in a non-trivial way, so I have to make this one 0, which means that the predator population should have size r divided by beta. Okay, how about the predator population? The change is p times, and when I take it out, I get epsilon beta f minus mu. Now, I want this to be 0, so I put this equal to 0, and f is equal to mu over epsilon beta. Now, I check on the data which I used in my pictures, and it should be somewhere here. Okay, so beta is 3/4. Beta is 3/4 in the denominator, so it's 4/3, and the same here. Then, let's see, epsilon is 0.2 and mu is 0.3. Mu is 0.3, epsilon is 0.2, and r, I need r right on at the start, 0.9. 0.9. So P, stationary, will be 3/10. Should I write it, or will I handle it? 0.3, it's 1.2. And over here, 3/2, 2, 3. F stationary is 1/2. 2, sorry, I looked wrong. 2. So these are the values of stationary points for my data. So what happens if I use them as initial conditions? That's a good question. Where is my graph? Here. So here I'm going to use for food. Where is food? Food. 2. 2 should be the value, initial value for food. And for the predators, it's 1.2. 1.2. Now I'm curious and a little bit apprehensive. Yeah, we got constant solutions. Wonderful. So the theory works. Oh, wonderful. When mathematics works, it's a nice moment. Okay, so we've got the predator-prey model, Lotka-Volterra, which is based on the exponential growth for the population of food, for the prey population. This is not exactly realistic. It's possible to introduce logistic growth here, but then these calculations become more involved. They are not as nice. So let me just show you some pictures. Here we go. We had this before. Okay, here. Let me just check. The differential equation for the food population has r times f. This is the exponential growth. And then we divide by k and multiply by k minus f. That's exactly the logistic growth. So that's it. The predator equation should stay the same. Yeah, it is the same. So let's just have a look at a picture of the slope field and some orbits. And we can see that the situation is now different, especially if we compare it to this picture. Here the orbits were not exactly ovals, but more or less like ovals, a little bit. Okay, they are elongated to the right, but more or less still oval. But over here, the orbits, they look more like triangles, triangles with rounded corners. And this is definitely not periodic, because as you can see, you are widening in. You pick some circle and start following the orbit, and you can see that you are not connecting to the same position again. You can be winding out or winding in, and it's hard to read it actually. So let's have a look at some particular example. So that's the typical shape for the predator and for the population of prey. And it seems to be roughly periodic. But now that I'm looking at it, the hills seems to be getting lower. So the amplitude is decreasing. So perhaps it's not periodic after all. Let's have a look at it. Let's look farther to the right. I looked at the time, 100 time units. Let's move it to 500 time units. Yeah, so definitely not periodic. How about triple it? Do we have time enough? Yes. So we really see that the situation is not periodic, definitely not. We were right that those amplitudes are getting smaller and smaller. But we are getting an interesting picture. It seems that the situation actually converges to a specific situation which seems to be stable. So this is an interesting outcome of our model. And you can play like that, and people do play like that. There are some points at this model which are felt that they are not exactly the best description of what's happening, especially the interaction between the prey and the predator. So there are some competing models. This Lotka-Volterra model, it's quite, let's say, popular because it's simple. So it gives you some answers which are not totally off, but people were trying to get better, more faithful models, but they are much harder to analyze. So there are many models, they differ, especially here in the interaction part. If you are curious, you can look it up. Very interesting reading and very nice playing if you program it and you try different starting conditions, different parameters, you start changing them, see what happens with the environment. So that's about it for this example, population dynamics. And that's the last example of the lecture. So see you next time, we will start a new chapter.